and good afternoon. It's my pleasure to talk about something that really excites me, that, as you mentioned, Joe, is about looking into the future. We don't anticipate the future, we make it happen, but we still need to dream about what we want to have happen. So I'm talking today about two transformational technologies we see are going to be very important to HPC and much of the rest of our industry. Now, I'm part of broader research efforts within Intel. There are two major components, first called components research, that is associated with our manufacturing group. Their job is to keep Moore's Law going, which they have for 30 years and anticipate another 30 years out of their research that explores well ahead of what ends up coming out in the process technology roadmap for products. I'm with Intel Labs. Our job is a little different. We're looking at taking advantage of some of those technologies as well as others in order to enable new capabilities for our products, as well as anticipating what the future would be or could be and building prototypes of hardware, software, silicon that try out those ideas and blaze a path or prune a path that isn't productive. We both work extensively in collaborations with the academic world in a range of ways, sponsored projects, research centers, and sometimes joint research collaborations, and I'll be talking about one of those particular ones in a few minutes. Now, quantum computing is actually an example of a collaboration of all three. It's a joint effort within Intel between Intel Labs and Components Research. I co-lead that effort with a colleague, Jim Clark, and we have a lot of fun with the fact that we're both Jim and the confusion and opportunities that creates. And a university in Europe, Technical University of Delft and TNO, a research organization in Netherlands. But first, let's talk about AI and neuromorphic computing. There have been tremendous advances in both computing architecture technology and algorithmic innovations that really are going to impact society in new and spectacular ways. I think we're just seeing the beginnings of the transformative power of AI. And today at Intel, we're using our strength in driving Moore's Law and our manufacturing leadership in order to bring a whole range of products to market, which you've been hearing about over the past day and a half, and undoubtedly will appear in the conference for the coming week, ranging from the Xeon line to FPGAs with new technologies like the Intel Movidius inferencing engine and the Nirvana technology for neural networks. Now, in our research, we're exploring both near-term and long-term ideas that are directions and possibilities for AI using these technologies, but also things well out ahead of them, and that's what I'm going to be talking about today. Now, the AI field is not static, it's evolved. I've seen many of the so-called AI winters, which I'm sure you have as well. And new technologies have come along, like logic programming, and not quite lived up to their imagined potential. Others, like neural networks, had a significant history and faded for a while until deep learning and some other breakthroughs revived them, actually, along with the phenomenon of big data. I remember when I was graduating grad school, which my dissertation involved aspects of AI, there were a whole bunch of techniques that were dismissed as impractical because they required too much data. And indeed today, training a deep learning neural network takes masses and masses of data and careful selection of that data. And so the combination of the two, I think, has made possible a whole bunch of things. Machine learning, that's, in my definition, a computer system that can learn without being explicitly programmed, like a neural net. Continues to advance with those kinds of breakthroughs, but we're also beginning to see things that were part of the more formal definition of AI. That is an autonomous vehicle or a robot perceiving the environment, interacting with the environment, taking action in order to achieve a goal autonomously, independently. It's something that really was in its infancy, now getting tremendous impetus from the usage models that we're seeing, like autonomous vehicles. Maybe it's just a case of the old saying of AI is just what we don't know how to do yet with machine learning. I expect that to happen here too. A lot of things will be incorporated into machine learning. Now, because of that analogy, because of the fact that we're reproducing the behavior of humans and animals, their natural intelligence, understandably, the architecture of AI systems has been very commonly brain-inspired. Neural networks themselves are named to that, even though they're really a long way away from the complexity and richness of the true biological neural networks. But as we learn from studying the natural intelligence of humans and other animals, I think we're going to continue to follow that theme because right now the capabilities, as marvelous as they are, fall far short of the capabilities and the efficiency of our 20-watt, 80 billion neuron systems that we carry around with us, particularly in our ability to learn and to adapt. So we're working on neuromorphic computing with a perspective of more than just brain-inspired. We're going over to the other end of the spectrum in a big way to try to create a device that mimics the behavior of a collection of biological neurons in the sense that it is event-driven. It does event-driven learning and adaptive behavior through silicon implementations of many of the same mechanisms. Now, it's a very different kind of compute from today's Xeons with multiple gigahertz frequencies and tens or hundreds of watts of power dissipation. The brain operates at low speed, less than 10, maybe at most 100 hertz. It's completely asynchronous. It's noisy and very fault tolerant because of the nature of the mechanism involved, but it's very energy efficient because of its spike event encoding method. There is not a lot of activity going on that isn't directly associated with the learning. It has massive connectivity. Neurons are connected to tens of thousands of other neurons, a level of interconnection that we really don't have in our current silicon products. And it is a case of compute in memory in a big way, because memory and computation are fully integrated. It is computing with memory. Rather than being programmed, it learns. It learns and adapts to its environment with much less training, with much less data than is required, sometimes with what we refer to as one-shot learning. Can we achieve that by reproducing the mechanisms? Next slide. Okay. The architectures we've begun to build are capable of all of the kinds of learning we've heard mentioned here. Unsupervised, that is, seeing patterns in data. Supervised, we're trained, and when we all go through training and learning about what things are, particularly early in life. Self-supervised, really using our senses to see the response to our actions. Who hasn't seen a child learn that their hand is attached and can move and that they are moving it, right? They see and connect with their intent and their action. Typical neuromorphic behavior. And reinforcement-based learning, where that feedback, that connection to the environment, changes, guides, influence without explicit presentation of correct cases, of correct input or output. And in fact, without necessarily correction of faulty output, with intermittent rewarding of the correct behavior or decision through consequences. So, ideal environment for all different kinds of learning. So, we've recently announced a neuromorphic research test chip. It's called Loihi, in a play on words, because Loihi is a volcano in Hawaii that's emerging. It hasn't surfaced yet, but it's on its way. It's building up. It uses an asynchronous spiking neural network to implement the adaptive, self-modifying, event-driven, very fine-grained parallel computation to implement that learning and inference with extreme efficiency. The event-driven aspect is really rooted in the fact that not just spikes are being sent out rather than manipulation of signals, but the timing of the spikes is part of what matters in learning. If my animation works here a little bit, it is filled with neuromorphic cores, which have many neurons in them. Those receive spikes from elsewhere in the network, and when the spikes accumulate and reinforce each other to a certain level, then the core fires and sends off more spikes to the neurons that it's connected to. And the timing of those spikes coming into the neuron make a big difference on what happens. If one precedes another, they reinforce each other. They reinforce the connection between those neurons. If it follows, then actually it will inhibit that connection, and the connectivity will decline. So very efficient and very time-based asynchronous signaling builds up the connections. Now, Loihi is not a product. And my notes here are out of sync. Okay. And so we can make no guarantee that it will deliver in real-world applications in the hands of folks the kind of value we expect in its current form. It's an experiment that we plan to share with leading academic, government, industry partners who also have an interest in this field. Because then we'll find out what they need, what they find works, what doesn't. We found in the past, in sharing test chips, and this is by no means the first one that we've done this with, that we learn a tremendous amount as others learn ahead of where we might go with our products. The test chip features include a fully asynchronous many-core mesh that supports a wide range of sparse, hierarchical, recurrent neural network topologies, where each neuron is capable of communicating with thousands of other of these artificial neurons. Each of the neuromorphic cores includes a learning engine that can be programmed to adapt to the network parameters during operation, the timing, the impact of the timing differences, for example. During operation, so supporting the necessary supervised, unsupervised reinforcement, other learning paradigms as needed. Rather than choosing one and encoding it, we put flexibility. And a typical approach in a test chip is to defer decisions, make them something that can be explored. It's fabricated on a 14 nanometer process technology and has a total of 130,000 neurons and 130 million synapses. Now, we've been using it in emulation, using an FPGA to reproduce this, and developed several algorithms that have shown high algorithmic efficiency for problems in path learning, constraint satisfaction, sparse coding, dictionary learning, and dynamic pattern learning and adaptation. And we have written a series of articles describing the architecture in detail and the software environment, the SDK that allows someone to use it, as well as our experience with these applications that we saw promise from. So watch for those starting in the first quarter when they are published. Silicon is coming out this month. So we're all excited about actually bringing it up and getting it working and getting it out into the world. So that's neuromorphic. So let me shift gears a bit. Of course, I brought a sample of neuromorphic with me and have been using it. It's a little harder with quantum computing, but actually because quantum computing is so counterintuitive, I'm going to be talking a bit in terms of analogies for a while. And this is one, my coin. Now, while in the air, is it heads or tails? Well, it isn't either. Neither heads or tails. It's both. It's a potentially either 50-50 that when you measure it, you'll find one or the other. That's one of the key aspects of quantum computing that we're building on in harnessing its power. Superposition, both heads and tails. Now, it isn't necessarily 50-50. If I had a weighted coin, it wouldn't be 50-50 odds that it would fall. So, yeah, it is a superposition, but it's a probabilistic superposition. And if you measure it, there will be different likelihood that one answer will come up versus another. The other really important concept from quantum computing is entanglement. That if you have 2 qubits and bring them together so that they form a system, so that they relate to each other, so that they correlate, then you get the combination of the states. Now that's a very powerful idea because what you get with 2 qubits is 4 states. With 50, you can represent more states than any possible supercomputer today can represent in its memory. If we had 300, we could have states that more atoms there are in the universe. That's the power of exponential representation that we can take advantage of. Okay, that sounds easy, but there's a catch. Fragility. They don't stick around in that coherent state, in that superposed entangled state indefinitely. There's any noise, thermal noise, other kinds of noise, imperfections in the manufacture, all kinds of things, or any observations, intentional or unintentional, cause a collapse to a particular state, probabilistically. So much of the challenge of building a quantum computer is dealing with that fragility in order to harness the advantages of it. But we're intent on doing that. Okay, how do we use it? Well, operating on all of those with some operations is the computation that we want to do. You take the entangled states in a register and you apply an operation to them to transform them, and you get a set of results. You get all of the results. And that's a bit of a challenge because you don't necessarily want all of the possible results of the particular transformations you're doing, unless your transformations include filtering, because if you measure them, you'll get one result. And if your set of filtered results includes more than one, you'll get some probabilistic choice of one. And in fact, if you indeed have an answer that consists of several possibilities, then you need to run it over and over and over again and capture the distribution. But there are many problems where a global attribute is what you measure, and therefore you get one value that describes the answer. That's why things like FFTs, quantum FFTs, are a very important tool. They give a global property of the input. Now, how many do, well, okay. Given that possibility, you get the potential for great speed up. Sometimes exponential, sometimes only polynomial, sometimes your overhead is, in the early part of your problem size, dominant. But there are many cases, there are enough cases where we've been able to identify algorithms that the payoff can be tremendous, particularly as we go to problem sizes exponentially. How many quantum qubits do you need? Well, a lot of researchers today are really working towards a particular milestone of 50 when we hit that point of larger state space than you can fit in the memory of today's computers. That's when it will begin to show its advantages, and you'll be able to run algorithms that demonstrate that it can do more, and that projection of that curve is going to take you up into areas that supercomputing won't be able to scale to. But we really won't be able to solve problems, small problems, until we get many more than that. Some chemistry, materials design problems are well suited to this, and we're exploring algorithms that are tolerant of error, reducing the burden of getting those fragile qubits to behave perfectly. If you have to have error correction is very costly. You have to have error correction on your error correction, and so you end up with something that could be thousands or millions of physical qubits necessary to reliably, fault-tolerantly represent one logical qubit. It depends on a lot of things, including the error correction technology you're using, and that's a major area of research today. But to do a commercial scale system with fault-tolerant operation, which is what you need for the cryptographic operations people are talking about as one of the major motivations for this area, is millions of qubits. And that will also be where machine learning becomes realistic, because you'll only get probably polynomial speed up for that. By the way, one other catch worth mentioning for this group, given you've been talking about big data, how do you get data from the outside world into that superposition entangled state? This superposition entangled state has tremendous representational capability, but preparing it is one of the big challenges of quantum simulation, and no one has found a good way to take raw data, images, for example, and efficiently put them in that representation. So there are many areas to pursue to exploit the benefit. What will a quantum computer look like? Well, perhaps something like this. The fragility of the types of qubit, most qubits, means that you want to keep them away from thermal noise, and so they're in refrigerators that go down to extremely cold, 20 millikelvin, very near absolute zero, and isolated from the environment with vacuum and metal shielding. Everything possibly eliminated you possibly can, because it would disturb your system and cause it to collapse. That, plus the fact that you need control electronics, error correction electronics, a whole new software architecture, different kinds of algorithms, mean you won't be getting a quantum cell phone or a quantum laptop. These are HPC accelerators, and they'll be in the data center or in the supercomputers, probably in the supercomputers first. How they talk to the supercomputers, how they're integrated with them, is another important area of ongoing research. Now, as I said, we're building the capabilities to build a computer, a quantum computer, and we're in the second year of that research collaboration I alluded to with QuTech and TNO in the Netherlands, and have been making significant process improvements. We are studying two types of qubits. One is more mature, the superconducting qubit, which is a very high quality microwave circuit in resonance that you shift in state with microwave pulses. They are the kind that are being used by many others in the field, like IBM and Google and Rigetti. They are more mature technology, but they're big. They're macroscopic. They're not nano, they're not even micro. You can see them with your naked eye. Getting large numbers of them then would be a challenge of connecting together many chips. Second type we're looking at are silicon spin qubits. You might think of these as a single electron transistor that's kept in a magnetic field with the orientation of the spin as your information. Up would be a 0, down would be a 1, for example. These are similar to conventional transistors that we make every day. And so we should be very good at making them, and more importantly, they're very, very small. And so we should be able to put many of them together. So scaling with the numbers that I had quoted earlier of needing for error correction, these hold promise, but the control of them, the calibration of them, et cetera, is not as mature as the superconducting. So we're looking at both. Now, you could have the qubits, and you still wouldn't have the supercomputer. You really need a full system, as I mentioned before. So we are doing top-to-bottom research with Delft and other partners, looking at applications, because we don't want to just work based on simple metrics like coherence time. Those are important for devices, but not enough for a system. We want to be designing and measuring our behavior in operations per coherence time that you can achieve on a real algorithm. And we want to have representative algorithms, because our experience in HPC and elsewhere tells us if you design with too narrow a view, you will not serve the future workloads well. You need to design based on an understanding of how it's going to be used in depth. In order to experiment with the algorithms, we need simulation. So we have functional simulation that actually is an HPC application. We have run on Stampede and on the Edison computer in order to be able to simulate running up to 42 qubits. Others have taken similar approaches up higher. Former intern and part of our collaboration on the first one has gone off and done 45. The point is, every additional qubit doubles the amount of memory you need, and the computations we want to do sometimes push well beyond the coherence time of supercomputers before you need to deal with an error in the system. So we do limited, but still much more simulation than we're capable of with hardware. We're also working on compiler technology, building libraries, and a major effort on the control electronics, because right now they are all outside the refrigerator in racks. It means running coax cables, 2 or 3 coax cables per qubit into that fridge, which obviously doesn't scale. So we're designing, with the help of experts in cryo-CMOS in Delft, integrated circuit to go into the fridge. And so that connection can be very intimate, very close, to drive those RF pulses at the just 4K level, a notch up in the hierarchy of refrigeration. We're focusing on the superconducting qubit program for now, primarily. We've built in a relatively short period of time, a progression of fully packaged chips. And in parallel, we optimize the performance of one size while we are scaling to the next size. They've been designed, co-designed actually between our fabrication team, our packaging team, and our academic partners. Academic partners know the control and design of qubits. Our packaging team has been inventing technologies to deal with the extreme cold and the RF signals that mustn't be interfered with. It's a very much an example of co-design. In the next 12 months, look for larger packages, as well as the first appearance of some silicon spin qubit results from our advanced 30-millimeter wafer processing line. We'll be also, in the system level, coming out with that cryogenic RF control RC, a full end-to-end system performance simulation, as well as continuing to build our repertoire of not theoretical mathematical algorithms, but material science, machine learning, other real algorithms. What's the implication for this group? We're talking about the future. Well, I think the implication is that get ready for another shift in thinking. Gone are the days when everything was done with conventional programming, where you were basically working with logic to write down how data was being manipulated in an abstract machine. We've begun to learn how to apply this new black box idea of deep learning with neural networks based on training, but we have to get our head around using that differently. Neuromorphic is going to require another change of thinking. How do we take advantage of that very dynamic, event-driven model and the extreme connectivity in order to get the benefits? And quantum, where, as I said, we're dealing with all of the data at once, but needing to select and measure with new kinds of operations in entirely different states. So it will take another change in thinking, not just in our designing it, but in the software community learning how to use it. Right now, all of our programmers are computational physicists. We hope that it goes beyond that as a market. So, exciting to be working on the future and encouraging. We really believe that the future that we're looking forward to is very bright. Thank you.